For centuries, human intuition relied on the assumption of a continuous, objective reality. In this classical view, the physical world is a solid environment that exists independently of any observer. A mountain remains a mountain whether or not anyone is there to climb it. Modern physics has revealed a far more rigid and restrictive foundation. At the deepest subatomic scales, the fluidity of nature disappears. In its place, we find mathematical constants and quantum rules that dictate exactly how matter and energy can move, interact, and exist. Curious tone. These paradoxes suggest that the universe may be governed by the same engineered constraints found in a massive rendering engine. To test this hypothesis, we have to look past the physical appearance of the cosmos and analyze its laws as fundamental hardware limits, efficient software optimizations, and system artifacts. The evidence for hardware limits begins at the smallest possible scale. In 1899, Max Planck identified a fundamental floor to reality. The Planck length represents the smallest meaningful unit of space, approximately 1.6 times 10 to the negative 35th meters. Below this threshold, distance itself ceases to exist. Time behaves similarly, operating in discrete ticks called Planck time. This reveals a universe that cannot be infinitely subdivided. It is mathematically quantized into a finite grid. Digital environments rely on this exact architecture. A simulation running at infinite resolution would require infinite computational power. By quantizing space and time, the universe becomes a tractable, finite system, one with a built-in resolution. Albert Einstein's special theory of relativity established a second limit, the speed of light. This isn't just a speed limit for photons, it is the maximum rate at which information and causality can propagate through the fabric of space. In a multiprocessor system, information takes time to travel between components, creating a mandatory latency. The speed of light mirrors this processing lag, enforcing a universal clock speed that maintains the consistency of the entire system. This computational signature extends to the particles themselves. Physicists studying the mathematics of quarks have identified embedded structures identical to the error-correcting codes used in modern web browsers. These specific binary sequences exist to prevent data corruption during transmission. A fixed resolution, a processing limit, and built-in error correction align perfectly with the technical requirements of a digital processing system. Efficient simulations also require software-level optimizations. The double-slit experiment reveals that quantum particles exist in a fuzzy state of probability until they are measured. The act of observation forces the universe to collapse these possibilities into a single definite state. Modern game engines use occlusion culling to achieve the same result. The system saves processing power by only rendering objects currently within the player's field of view. A tree on the other side of the map remains a low-resolution placeholder until the player turns toward it, at which point it is rendered in full detail. This optimization may explain the holographic principle. Theoretical physics suggests that the information defining our three-dimensional universe is actually encoded on a two-dimensional surface at the boundary of space. A digital character experiences a three-dimensional world, but that world is generated from flat strings of information. Our perceived depth and volume appear to be a projection from a lower dimensional dataset. The universe prioritizes computational efficiency, refusing to finalize reality until the moment it is observed. Any sufficiently complex simulation will produce anomalies, detectable errors where the underlying code becomes visible through the rendering. Quantum entanglement, where distant particles instantly mirror one another, appears to bypass the speed of light. However, in a simulated framework, these particles aren't communicating across space. They simply share a single memory address, updating simultaneously because they are the same piece of data. Dark matter represents another potential artifact. It exerts a gravitational pull that shapes galaxies, yet it is completely invisible and non-detectable. It behaves like a background process, a computational placeholder that generates physical effects without requiring a visual render. Astronomers have also identified unexplained temperature patterns in the cosmic microwave background. These alignments suggest the presence of a discrete underlying grid, the kind of geometric signature expected from a world running on a computational lattice. These phenomena represent the shortcuts and artifacts inherent to a system built on information rather than solid matter. Philosophy bridges the gap between these physical observations and statistical reality. Nick Bostrom's simulation argument suggests that any civilization reaching a high level of technological maturity would eventually run billions of highly detailed ancestor simulations. If these virtual worlds are possible, simulated consciousnesses will eventually outnumber biological ones by a massive margin. Probability dictates that we are far more likely to exist within one of these trillions of simulations than in the single version of base reality. This statistical likelihood is now accepted by prominent physicists and technologists, many of whom estimate the odds of us living in base reality at 1 in billions. This changes our understanding of the human mind. Evolution selects for organisms that see reality usefully, not accurately. Like a computer's desktop icons, our senses provide a simplified user interface for navigating deep, complex data structures. Our subjective experience is the result of the simulation rendering itself at the point of observation. The anomalies of quantum mechanics are the logical results of a world built from mathematics. By studying these limits, we are beginning to understand the architecture of the system.